Hi, I'm Dmitry Selemir, and this is a video version of my article published on Towards Data Science. It's called A Fresh Look at Clustering Algorithms. Just to provide a little bit of context before we dive in, so the problem originates in something that I've been looking at a couple of years ago, is trying to analyze raster files or LiDAR data. Yeah, you might know it by that name. Essentially, it is a collection of points collected by firing a laser from a plane at the surface and trying to measure the response and get the height of the whatever objects it finds there. So it can be buildings, it can be mountains, it can be roads or rivers or coastlines, green spaces, tree coverage, anything. Um, so it turned out that in order to determine the outlines of all those objects, I had to use a clustering algorithm of some kind. I didn't like any of the available sort of commonly known algorithms that I could use. So I had to develop something specific for that particular problem because of its peculiarities. But it turned out that this algorithm can be extended to a much more generic case of problems. And so essentially this article is the result of that. It's still work in progress, even from the time that the article itself was published and this video is recorded. There's been some significant progress. So the code presented here will have slight differences. I'll actually go in a little bit more detail in a couple of places than I did in the article. So if you have read the article, so this will still be potentially quite useful. Okay, let's dive in. So the first thing that we need to do is we need to define the kind of parameters going into the problem. So we need to define the space we're working with. So one parameter that I found particularly helpful and that I'm using as an input now is the kind of the number of divisions we need to do along each of the dimensions of the problem. So kind of how many unit cells we need essentially. If you think about it, we can basically represent each observation as a unit cell in our space. We try to make it as compact as possible, kind of spread them as uniformly as possible. And the size of that unit cell essentially tells us that if we go anywhere below that, we are risking um, getting a lot of spaces where there'll be no observation at all. Or we'll have just one specific observation. And that's for clustering obviously not particularly useful when I'm going to find anything. So this is, you can think of this as a critical value. This is particularly important for the problem like the one I described earlier, because we don't actually have points really bunched up together and sitting in the same place. They're evenly distributed. And the difference between the cluster and non-cluster is you have those points measured within a cluster and you have absence of those points outside of its boundary. So the problem is slightly different to the traditional sort of clustering setups that you're probably used to. But the measure itself is actually quite instructive for all kinds of problems. So I find it quite important. So that drives our initial setup. So let's get down to the algorithm itself. So what we're actually doing is we are trying to determine the cells, the elementary cells sitting in space where of our observation, and we can have as many observations and as many dimensions as you want. So for example, this could be applied to analyzing text, which is transferred into a vector format, and each dimension there, each variable there can be an input into this model. So what we're trying to determine is find those unit cells which are populated above a specific threshold, and that's another input that we're going to be using. And then we count all of those, and we're trying to represent this as a tree structure, the graph structure rather, and each cluster will be sort of a complete outlined collection of those unit cells. So in graph speak, this will be a kind of unconnected trees. So essentially all we do is we normalize everything so that all the uniform or kind of the continuous variables are in the 0 to 1 interval. Then we multiply each by that divisions number that we came up with. So we take the integer part of that and then do the multiplication. So this gives us discrete cells in our space. And then we just count the number of observations in each of those unit cells we created that way. Finally, once we have those, all we have to do is go through, basically we pick one, we go through all of the neighbors until we run out of them. And that gives us one unconnected tree, then we pick the next one, then we pick the next one, and so on. So this way we can propagate throughout the entire space and determine how many clusters and actually have a complete and fairly accurate representation of what's inside those clusters. Okay, so let's get down to it. A bunch of libraries that we need to load. These are all pretty standard. Apologies. So NumPy and Pandas, I'm actually going to do most of the stuff within NumPy because it's a lot faster. So Seaborn, Matplotlib, the usual sort of stuff for for plotting, and I'm using clear output to make the function outputs just status updates a little bit more compact. We'll use time to measure the performance of the main functions and compare them to some of the sort of out-of-the-box clustering algorithms. And we use its-tools package as well in one small place, and it's all basically to try and avoid loops at all costs. All right, so next thing we do is we'll create a dummy data set. We'll have basically a 2D problem as a toy problem. We'll have 4 clusters in it, and we'll stretch them in various ways. So this is all pretty straightforward setup. Let's quickly have a look at the numbers, how they look like. So we basically generate the x variable and y variable, and then we can plot them on all together. So we'll have these 4 nice clusters. 2 of them are kind of roundish, and 2 are quite stretched. And then, as in the first step of the algorithm, we'll normalize everything, and the final sort of representation will be the box from 0 to 1. So you see 0 to 1 on both axes, and still the same shapes, obviously. Right, so we've got 4,000 points there, and if we calculate our D parameter, the number of divisions we need, we come up with 63. So this is defined specifically by the number of variables that we're working with, and with number of dimensions. So in our case, it's 2. So we're going to use this D equal to 63, and we'll use tolerance of 70. What that tolerance parameter means is we essentially look for percentiles. So when we count the number of observations in each unit box, we're going to discard the ones below 70th percentile. So it's probably a good idea to play with this parameter for every problem. So in fact, if I reduce it to 50, depending on how our numbers were generated in the first place, we might actually get like one false cluster. So for some values that might actually happen. But in any sort of problem, you will need to play with those parameters to try and see what works best. In general, it's more stable than applying, for example, like an elbow approach when you're working with K-means, and then you're trying to look for different number of clusters and see which one's best. In this particular case, is just you will have in sort of some spaces where for some tolerance numbers you'll get a different number of clusters, but generally they should be quite stable. All right. So next step is we create a NumPy array out of our data frame. So we only need our x and y there, and we stretch them, we turn them into integers, and then the next step is what we're doing is we are creating string IDs. This might not be the most optimal solution for this, to use the string IDs for each observation, but it kind of works for this. It works for other problems. For much more general, much larger case, I will probably think about replacing that with something else, or building the algorithm without having to resort to IDs. But essentially all we're doing is we're padding each number to make sure that it's the same length as the length of our dimensionality parameter, so or divisions parameter rather. So in this case it's 63, so we need two numbers in each one. So we're padding them with zeros if we need to, and then we concatenate them together into one string. So in this particular case, we'll end up with 4-digit string representations of each observation. Right, so this is pretty quick, and then we basically do the counts and create this tree dictionary. You'll see that in the actual function when I wrap this up later, I won't need to do that anymore. So will be enough to just use the unique numbers and the counts. Okay. Next, we calculate this threshold. So we basically look at all of the counts, and then we apply our tolerance and come up with the minimum number. And final step, we prune the tree, so we remove anything that sits below those counts. Okay. Counting trees. So we come to the most interesting thing, that's actually not covered in the article in that much detail. So it is basically a implementation of breadth first search algorithm of some kind. So it's not quite the classical version of it, but essentially all we're trying to do is we're trying to count those unconnected trees. So what we're doing here in the first cell here is we create number of stresses. So we're going to be taking each ID, and then we're going to be trying to figure out what the nearest neighbor cells are, or of that specific cell that we've selected. So we do that by just adding ones and minus ones or zeros to its coordinates. So essentially we'll be taking a string ID, dissecting it back into to integers, we're going to be stressing them, and then converting them back into the IDs. So that's happening later in the function. I'm going to show you exactly how it's done. And so this will just give us a number of arrays, or rather lists, with stresses that we need to apply. And obviously we don't need to apply 0, 0. So this is all we've got there. And that depends obviously on the number of variables we have in our data set in the first place. So here we have 2, so we basically have lists of length 2. If we have more, then we'll obviously have more numbers here. Right, so the function that wraps everything together to do the BFS, what we need is an array where we keep all of the IDs that we're working with. So this is all IDs. We're actually going to be removing them one by one as we go, and as we find neighbors and check those neighbors, we're going to be removing them as well. So this array is going to shrink to 0 towards the end. And then as we extract one ID, we pass it into this toCheck array. And we also pass there all of its neighbors. So all we're doing is we're taking the neighbors and we go through them one by one and repeat that process. And we do that until we run out of options. So basically, the neighbors being checked are not actually in the data set. So this is happening here in this part. So we basically grab the IDs. We basically apply the stress and finally convert them back to strings in here, and we finally add them into this toCheck array. If there are any. So we also have to check that they do actually belong to the data set in the first place, because we only want to work with the ones we identified as meaningful, so sitting above this threshold. So once we've done that for the first one, then we recycle through all of the neighbors, and we repeat the process for each of the members of the neighbors. So in the classic algorithm, we use queues for that. So we're always trying to go as wide as possible, but we don't actually have to do it that way here because I mean we still do kind of go by first element at all times, but actually we can grab any element. So we could use a pop function if we wanted to. Right, and the visited array is used to keep track of what we have already seen, so we don't check anything twice. Okay, so the outcome of this will be a collection. So we output it as a dictionary, and each key of that dictionary will be one specific element, which we chose basically randomly, where they just came up first. And then under that key, we'll have the list of IDs of all of the elementary cells that belong to that cluster. So essentially, we'll have a collection of clusters and all its components. And we can then relate those clusters to the original data and mark up our entire data set with the cluster that those points belong to. All right, so let's commit that, and let's do the calculation. So that was pretty quick. We found 4 clusters as expected, processed all of the IDs, and now I can just plot the result. So let's see what's happening here is we didn't actually assign all of the points to our clusters. We found their centroids, it's pretty close at least. We identified how many clusters, but what happens is all of the points that happen to be in the cells that were below the threshold that we defined were left out. We didn't actually try to assign them at all. So now after this, the next step will be to go through all of them and try and assign them to the correct cluster. There are many ways you can do this, but for kind of ease, I guess, and for the speed of the calculation here, I'm just doing the nearest distance. So it's essentially kind of a least square approach. So this is not too dissimilar to what KMeans is doing. And you'll see later that as a result, the final representation, the final result is actually very, very similar to the one obtained from KMeans. Okay, so we're doing this here. So we are calculating the centroids, and then we cycling through the entire array and calculating the distances. And I'm not bothering taking the square root, so just the squares. We find the minimum, and then we assign each point according to the minimum distance to a cluster. So do that, and then we do plotting, and now it's all nice and color-coded, nothing is left out, and all of our points are classified. Okay, so now I can wrap this into one function. Actually, there are going to be two functions. So one is going through all of the steps that we just kind of cycled through and calls find trees in the end. You'll see that here we don't really bother using the tree results. We basically use unique and counts. And we'll commit that. We'll also use a function for this cluster attribution, the one that we used here. We just wrap it into the function that will call the whole thing. And then we define a fit function, which combines all three all together and provides us with one outcome, one sort of classification. So let's measure some times and compare it to some of the sklearn algorithms. So let's run that. We've got 207 milliseconds, not too bad at all. In fact, if we disable some of the results printing, this comes down to about 89, I believe, so it's relatively quick. Okay, once again, final outcome. So this function that's basically the same as we had there, just on a slightly larger scale. So I guess one thing to pay attention to here is we're not very good in a couple of areas, like around here. These points should have probably been assigned to this cluster, and this point probably more appropriate for this cluster. This is actually the consequence of us assigning the points according to the minimum distance criteria. So if we use something else, so something similar to Gaussian mixture, for example, then we'll get a different result. So this is something to bear in mind. So that final step, that final function that we applied with attribution, there's some flexibility there, and there might be better approaches to doing that. Okay, let's have a look at what other models are able to do. So affinity propagation is the first one. This one happens to be the slowest. I think it takes about 20 seconds to calculate. And you see that the result is also somewhat underwhelming, but I'm jumping a little bit ahead. Okay, 28.3 seconds. Okay. So when we look at the results, it really is all over the place. It wasn't able to find clusters properly and divided them into all sorts of sections. You can play with the parameters of this one, but it doesn't really help all that much. So I'm not a big fan of this particular method. The next one, agglomerative clustering. This one actually needs to be told how many clusters you have. Again, not ideal. Slower than what we've got, so we're currently still first, I believe. And this one did okay. I mean, it has its own problematic areas, like here, and I'd say here as well. And depending on the numbers, you'll see that there's some occasions where kind of they all flow into each other. So not ideal, but it's certainly better than the previous one. Moving on to Birch. Before I started this exercise, this was actually my favorite, but it doesn't perform nearly as well as I thought it could. So again, it's slower than what we've calculated. and it also has its own problem areas like here and again here as well. Still, it was able to uphold the four clusters, which were actually the input. So DB scan. So this one doesn't have number of clusters as an input, so we should like it more. It's quick, but it's not particularly good at actually recognizing the clusters. So in fact, it found loads of clusters here, and yeah, the result is not particularly useful. KMeans, this is the classic one, and you'll see, so this one is actually faster than us as well. So this was faster and this was faster, so we pushed into the third place. Let's have a look at it. So this one looks very, very similar to the output we've generated. So even kind of these areas and these areas are all the same. And that's essentially to do with the fact that our final steps are exactly the same. We're looking at the mean square error. Mini batch K-means exactly the same results, a little bit slower on this specific data set. I guess it has its own advantages on larger data sets. The result looks exactly the same here. Minshift, another algorithm that doesn't actually require the number of clusters to be fed into it. It's a little bit slower, and you'll see that the result here is also not that impressive. So in general, the current algorithm in Scikit that don't have the number of clusters as an input really struggle with this data set. So you see it actually found three clusters. One of them is kind of divided neatly into two parts, so not really where we want it to be. Spectral clustering, again driven by the number of clusters. It's again slower than us. And again, not without its problems. So this area didn't really do that well, and here as well, arguably. Finally, Gaussian mixture. This is probably the best of them. It's quite fast, and the results actually look the best out of the lot, in my opinion, at least. I think it's outperforming what we're doing a little bit. Again, it has the that problem of having to be told how many components there are, how many clusters we're looking for. And if you give it the wrong amount, it will find exactly that amount. So potentially some kind of combination of our approach in this is probably something optimal. So let's now calculate some. Actually, we'll calculate again to get rid of the warning. So the warning is to do with pandas not liking the rows and columns in multiple plots. So I believe they're actually looking to fix that, but it is what it is for now. So this is just everything combined all together, so you can look at them side by side. So the last one, this is density trees, the algorithm that I've described. This is the Gaussian mixture, and so on. So they'll sign up here. I guess the main conclusion here is that out of all of the clustering algorithms that we looked at, the ones that should be able to figure out the number of clusters automatically themselves are struggling, at least with this particular data set. None of them were able to do it. I think in terms of comparisons between the methodology I described and some of the better performing cluster algorithms, the ones that are told how many clusters we have in the dataset, how many we're looking for, I think we're on at par with most of them, with the better of them, in fact. And I would say second only to Gaussian mixture in the quality of the recognition. And also time-wise, I think we ended up with fifth overall compared to all the other algorithms. Now, in terms of time, I have been making some progress. So my tree algo is definitely not optimal. So I made some improvements since the article came out. So if you read the article, I basically said that the calculation for the entire sort of 2000 points by 2000 point matrix, so 4 million element matrix describing an area of central London, took something like 5.5 hours. In fact, now it's calculating the same data set is being worked on for only 29 minutes and 30 seconds. So it's still a lot, but a lot less than it used to. And there's a massive area of improvement that kind of I've identified already. So I reckon it can be reduced to minutes, if not seconds. So there's plenty of scope for improvement without even going with GPUs or parallelization or anything like that. So just algorithmic gains can be quite significant. And I think they need to be explored first, obviously. So this is it for this article. I hope you found it useful. Thanks very much for listening and following through with me. And a huge thank you to Towards Data Science for publishing this and for getting me to do this video as well. All right, take care.